Another application of the properties of sums comes with the sample mean. So earlier we looked at the sample sum of a collection of random variables, all of which had the same mean, mu, and standard deviation, sigma. And so the sample sum was the sum of our collection of random variables. The sample mean then is the mean of our collection of random variables, which is 1 over n times the sum. And we can note that the sample mean is just a linear transformation of the sample sum. It's 1 over n times the sample sum. Earlier, we found that the expectation of the sample sum was n times mu, and that the variance of the sample sum was n times sigma squared. And so we can use the properties of linear transformations with variance to determine the expectation of the sample mean and the variance of the sample mean. So the expectation of the sample mean is 1 over n times the expectation of the sample sum, which is 1 over n times mu, which is just mu. So the expectation of the sample mean is the mean of our random variables individually. The variance of the sample mean is 1 over n squared times the variance of the sample sum. And so that's 1 over n squared times n times sigma squared, which gives us sigma squared over n. So the variance of the sample mean is sigma squared over n. That tells us that the standard deviation of the sample mean is sigma divided by the square root of n, which we get by taking the square root of sigma squared over n. So you may be wondering what the point of all of this is. Great, now I can compute the variance of a sum, but what am I going to do with it? Well, let's take a step back. So oftentimes as a data scientist, our goal will be to estimate some characteristic of a population. So for example, we may want to estimate the average height of undergrad students at UC Berkeley, and to do this, we will typically collect a sample of students and use the sample's average to infer what the population average is. The thing is, we only collect one sample, but since we typically sample randomly, our sample could have come out differently. There are any number of possible random samples we could have collected. The one we collected has a specific mean, but if we collected any one of these other possible samples, we would have had a different mean. And so it's important to not just look at our sample's mean, but also to look at the distribution of all possible sample means. One property we just proved was that the expected value of the sample mean is actually equal to the population mean. So when we're sampling at random, on average, our sample's average will be equal to the population's average. And the fact that the sample mean satisfies this property gives it the term unbiased. So we say the sample mean is an unbiased estimator of the population mean. Don't worry too much about the term unbiased right now. We will reintroduce it later in the semester when it becomes more relevant. So now we have this notion of the sample mean being a good estimator of the population mean. But what about the variability? Another thing we also proved was the square root law from data 8, which said that the standard deviation of the sample means distribution is the population standard deviation divided by the square root of n. So as you increase your sample size, the standard deviation of the sample means distribution will decrease. So over here on the right, we have the distributions of two different sample means, both drawn from the same population, but with different sample sizes. Due to the square root law, we can tell that the yellow distribution corresponds to a larger sample size, because as we increase n, we increase our sample size, the standard deviation of the sample mean decreases. And so the point of these couple slides was to tie in the things you learned in data 8 about the square root law with the random variable framework that we've presented to you now in data 100. The last instance of that will be us talking about the central limit theorem, which you also saw in data 8, which said that regardless of the population that you're drawing from, the distribution of the sum of an IID sample is roughly normal if the sample size is large. Now in data 8, they didn't say this exactly. They instead said if you draw with replacement. But we saw earlier in this lecture that when you draw with replacement, your random variables are IID. And since we now know that the sample mean is a linear transformation of the sample sum, the sample mean is also roughly normal, just with scaled parameters. So that's the central limit theorem again. We won't use it a ton in this class, but it's nice to be aware of it and see how it ties in to random variables.